Actually, I will mention that, but yes. So Zoltan is software developed at Sandia. I'm from Sandia National Labs. It's also available as part of Trilinos. Trilinos, I think there was a tutorial yesterday about Trilinos, yeah. Right? Yeah. So Trilinos is actually a very large framework with lots of different packages. And I also very tempted to mention that one of the packages with Trilino is called Anasazi, and Anasazi can solve eigenvalues very similar to the SLEPC that was just presented here, actually. So, if you're using Trilinos, you can use Anasazi, and you can do pretty much, the same thing you can do with SLEPC.
Right.
Okay, so anyways, back to Zoltan. So this is work with my colleague Karen Devine at Sandia. So I'll give an overview of Zoltan. You can do load balancing, ordering, coloring. I'll go through as much as I have time to go through here. This year, we're actually not doing a hands-on session for Zoltan because it's a little bit hard to do in a way to convey the capabilities. Instead, within the slides, I have embedded a lot of sort of technical pseudocode fragments. So when you have the slides, it should be a good starting point for figuring out what to do in your own code. So I will go through that fairly quickly, but you have it in the slides for your reference.
Excuse me.
Yeah.
Your microphone is in the wrong place. Let me fix it. All right.
Okay. Thank you. So, well, I hope this works better. Everybody here can hear me, but I don't know about out in the cyberspace. Okay, so Zoltan Toolkit, what does it do? Well, a very broad definition of what Zoltan does is it's a library of data management services for unstructured, dynamic, and adaptive computations. So, of course, that has a very broad title. So more specifically, there are certain capabilities that are common in scientific computing that's provided through Zoltan. And, so where's this pointer, actually? I thought you said you had one.
Yeah, no, give it to
Okay, well, I'll keep going. So partitioning of data, load balancing is probably the main capability in Zoltan. But over the years, we have also added other things like graph coloring, matrix ordering, and also data migration. When you do parallel computing, you must move data between processors. This is, of course, related to the load balancing problem. And there's several other things here in the bottom of the screen that I'm not actually going to talk about because they tend to be more internal features. Oh, hidden. Okay, okay, thank you. Thank you, Tom. Okay, excellent. Excellent. Okay, so what is the context for how people use Zoltan, or how it should be used, I guess? So it's designed to do parallel computing in the distributed memory context. So we are assuming that each processor has its own memory space and its own local data, and that moving data between the processors is expensive, so you want to avoid that. So a lot of codes are built on this model where you could decompose your data to processors, and then the owner computes, right? That's actually a phrase, owner computes, right? So you do as much local computation as possible, then you need to do some message passing as well. So that, oops. Yeah, so the point then is that the data distribution really defines the work assignment. And of course, you want to distribute the data between the processor in an intelligent way, so you get load balance and you reduce communication and things like that. And that's what Zoltan is all about. It's how to produce a good data decomposition for you. And I call it partitioning. Some people call it domain decomposition, but it has many names. So Zoltan, it has been around for about 12 years now as a software project, but it's been available within Trilinos for the last few years, well, since version 9.0, and now we're up to 11, I think. So this has been a few years. So what do you need in order to run Zoltan? Well, you don't need very much. That's one of the nice things about it, is that it doesn't have a lot of dependencies. So you need a C compiler, you have these build system, AutoTools or CMake, and then, of course, if you want to run in parallel, you need MPI. That's really the standard for message passing. And feel free to interrupt with questions at any point.
Question.
Yes?
So does it depend on any other Tilinos packages at all?
No. That's actually somewhat unique within Trilinos because there are a lot of packages in Trilinos, and often they have dependencies on other packages. But because Zoltan was initially developed as a standalone, separate package, it has no external dependencies except for MPI, right? So, yep. So in fact, a lot of people use Zoltan by itself without the rest of Trilinos. You can actually get the code and compile Zoltan by itself without knowing anything about Trilinos if you want to. So you can use Zoltan with PETC or other frameworks as well.
And they are actually used. It is actually used. It's just that, you know, the end user doesn't see it, but the calls will be there. From PETC.
Yes. In fact, this is true that there is an option, at least in PETC, to use Zoltan under the hood.
Yes.
Yes, that's right. Okay, so let's say here's just to show you that actually Zoltan is used by a lot of different types of applications. So it doesn't depend on any particular. It does not target a specific application area. So actually, I could have even more examples here, but these are just some of the things that I know Zoltan is being used for, like circuit simulation, particle, molecular dynamics type of things, multiphysics, crash simulations, and more generically, it's often used by other libraries, not by the end application. So like linear solvers, preconditioners, or adaptive measure refinement can often use Zoltan underneath as well. So, and Zoltan has really been developed for the high-end computing, right? It's not something you want to use on your laptop with 2 cores or something. So it's really high-performance computing. And here's a slide of we just collected information from collaborators and other projects that have been using it to do like cutting-edge high-performance computing. And okay, so the first column I want to get to, the different types of algorithms within Zoltan, you can ignore that for now. Here are some of the codes or applications that have been using Zoltan, and the problem sizes. This is just what I want to show you, that if you have like a computational fluid dynamics on 1 billion elements, and you want to run on like 4,000 processors, then you have a supercomputer, then Zoltan can help you. Just as one example, and there, actually, as you can see, number of processors can go up to, well, I think we run even more actually, 24,000. Oh, okay. Over here, I see even 160, 260. Oh, okay. So let me just explain what I mean by number of processors and number of parts. So in parallel computing, typically you decompose your problem, so each processor gets one part of your problem. So these parts corresponds to like subdomains or parts within a partitioning problem. And typically, number of processes and number of parts are the same, but actually, if you have 2 columns there in this table, because in Zoltan you could decouple it, because sometimes you can solve the partitioning problem on a smaller set of processors, and then you save it to a file, and then you actually do your big run on a larger number of processors later. So it depends how you do things. But some people do it that way, and then that's why you can see that sometimes, here at 4,000, but actually you solve a partitioning problem of 4,000 processors, but actually you run it 160,000 processors later. So you can actually do that. So Zoltan has had DOE funding for many years from various different sources. SciDAC has provided a lot of the funding for this over the last few years. One of the projects that Zoltan has been heavily involved in was ITAPS, which actually now has been folded into this fast math project some of you at least know about. So what will you do it? Okay, so mesh partitioning is a very common application of Zoltan. And there's also been hooked up to, we've been working with RPI, Rensselaer Polytechnic. They have a mesh database called this FMDB. And we have developed an interface around Zoltan called iZoltan to work directly on meshes. And we've done mesh partitioning for up to 1 billion elements in this way. And it's used also by many other labs like SLAC and the Princeton's plasma physics. And here is just, again, another example of an application that uses Zoltan. This is, let's see. Okay, it says it's the CFD code FASTA. I think this is a simulation of blood flow through an arm or an artery. And anyways, the point here is that it's a large problem. The number of cores can go up to 128,000. And they managed to get very good scalability. This is a strong scaling, so the time goes down as you increase the number of processors. And this is, the compute efficiency should be close to 1, and it is pretty close to 1. And of course, this depends on what algorithm you use, but if you don't have a good load balancing, you're not going to achieve this. So load balancing is certainly part of the reason that they managed to get so good scalability for these type of problems.
So when you mean static, so there is no adaptivity in the...
Yeah, okay, I asked you through that. So that two... Actually, I think these are two different bullets, right? Because up here I mentioned adaptivity up here, but down here is a static partitioning. And actually, I'll get to that in a couple of slides, which is static partitioning means that you have a fixed mesh, you have a fixed problem, and you partition it once, and then you never change your decomposition. In the adaptive case, you actually do a repartitioning and you move data around. So I believe that the table of results down here corresponds to this bullet. Actually, I'm sure we did this static partitioning. And we're actually for this particular example, static partitioning was sufficient to get good scalability. Did that answer your question?
Yeah.
Okay, and another show and tell slide here. So this was the work we did with the Stanford Linear Accelerator people a couple of years ago. They have a code called PIC3P, an accelerator simulation code that solves Maxwell equations, but with particles. So there's an electromagnetic field, and there are particles moving around. And I like, this is like my favorite animation. That's why I always include it. So this is a part of an accelerator, and I'm not a particle physics person, but this is known as the LCLS RF gun. And don't ask me what it is, really. But what I understand is that there is a mesh on this component, and there's an electromagnetic field. And in order to solve for the electromagnetic field here, we did a graph partitioning, which is shown in the sort of the background mesh here. We had to do a graph partitioning to get a good decomposition of the mesh. But then there are lots of particles. In fact, number of particles flying around it was up to, I think, 1 billion particles. So you had to use a very scalable, cheap type of method to figure out how do you assign the particles to processors? Because if you have 1 billion, you cannot afford to use the more expensive methods. So we used a geometric method where you just look at your coordinates in 3D space. And that's why the particles here, you can see different colors correspond to which processor that actually is computing on these particles. So this was done by Arno Kandel at SLAC. And so these particles actually, well, okay, so these two pictures are part of the same simulation. Really, this is a close-up of some particles that are flying around here. And so within, it's a multiphysics simulation, and you actually use two different data decompositions. So one that's like optimal for the Maxwell equations on the structure, and another decomposition that is more suitable for the particles. And with Zoltan, you can do the things. You can do one decomposition there, and you can do one up there. And then, of course, you have to adapt your code to work with this. But this is, so this can give better results than just doing a single decomposition. OK, so now I will mention some of the, the API and interfaces and so on. Zoltans are interspersed in the talk as we go along. So I mentioned that Zoltan can solve different types of problems. The partitioning problem is most important, but also other things, and like these other combinatorial problems, graph algorithms. And one good thing is that there's a common interface to each set of tools. So once you've written like the interface to Zoltan, you can solve a whole bunch of different types of problems. You don't need to have one interface for partitioning and one for ordering and so on. It's all the same way to get the data in the same way. It's what I call a data structure neutral design. This is really the way we decided to try to do object-oriented programming like 10 years ago before C++ was widely adopted. So Zoltan is actually written in C, but it's written in such a way that it does not really use explicit data structures, and we use a lot of function pointers and so on to sort of hide data structures, or not hide it, but to make it more portable and more flexible. So that has, and that's actually worked out pretty well. It allows us to support a wide range of applications and data structures in this way.
Fully support other languages.
Yes, and other languages as well, yeah.
Right, because if it's a C++ structure, then you have the problem that the objects are not visible.
Yes. So yes, and so I should mention that even if Zoltan itself was written in C, we also provide interfaces in C++ and Fortran 9095. So yeah, and that comes with the Zoltan distribution, actually. It's not something optional. It's actually, you have it. Yeah, OK, so next slide, right? So I knew I had it somewhere. So I think the external interface we try to minimize as much as possible. So I can claim it's simple, easy to use. I should say that, well, you need to spend a few minutes to figure out actually how to do it the first time. But once you understood how to do it, it's actually pretty simple. The startup cost is, it's could be confusing the first time. But yeah, it is callable from at least 3 different languages. OK, so what are the things that you as a user need to keep in mind? One thing is, remember we're talking about parallel computing and distributed data structures. So in order to distinguish different user data, we have this requirement that you need what we call a unique global ID for any object that you're going to partition or do any work with. So what are these objects? Well, I mean, like, this is the user's data. This is the data you want to distribute. So this could be elements within a finite element computation. It could be rows of a matrix. It could be particles in your physics problem. It could be lots of different things. And the most important thing is that, well, you need to have sort of a unique global way to distinguish this. And typically, these are just like integers corresponding to rows or elements. But they could be other things as well. So for example, some people like to use a pair of identifiers, first a processor number and then a local number on that processor. And Zoltan allows you to do this. So we don't, unlike like Trilinos or Petsy, we don't sort of insist on a specific type of numbering. You can just tell us what your numbers are. OK, so how does it work? Well, we use what we call query functions, which are similar to callback functions, which means that the application actually needs to provide specific information to Zoltan, and the application will need to write a small number of functions to provide this information. So for example, it will be these identifiers for your objects. What are your coordinates, or what are relationships, which could be like a graph model. You need to know which elements are connected to which other elements. So that's what I mean, like connectivity and other kind of relationships of that type. So yes, the application writes these small, simple functions, and there might be some small extra cost in memory and this function called overhead, but that's really in the noise. I don't think you need to worry about that at all. It's very small compared to other things in the application. So let's focus on like partitioning algorithms. What are the query functions that you need to think about? Well, if you have a geometry in your problem, which most people do, you can use some geometric algorithms, and then you need to have some query functions to represent the geometry of a problem, like how many dimensions do you have, what are the coordinates of your object, and so on. If you're working using a graph or connectivity-based algorithms, you need to have information about what edges and weights and so on. And I'm going to talk about that. We have graph models. We also have a hypergraph model, and I'm going to get back to that shortly. I'm not going to talk about the tree-based. OK, so once you have implemented these query functions, then it's very easy to try different types of algorithms, because you might not know which algorithm is the best one, because we actually have a collection of different algorithms. But they all use the same data or the same query functions. So once you have those in place, you can easily switch between algorithms by just changing one parameter to try different things. So the flow in Zoltan would be, or in your application using Zoltan, that's what I mean, right? So your application is here. You would initialize Zoltan, and then you would select a certain method that you want to use. You would need to write this query function, and you need to tell Zoltan that they exist. That's what we call to register the query functions, but this Zoltan set function. So it's setting a function pointer, essentially. And then you would typically will partition your data, you'll move your data, and you do some computations, and then you might loop around, and you might want to redo this again. And then at the end, when you're done, you have to clean up the things by doing this Zoltan destroy, which will free the memory that Zoltan uses, so you get a clean exit on your program. And then here's a table of commonly used of these query functions, where these and then it looks like there's a long list, but you actually don't need all of this, right? That's the nice thing, right? So on top here, these two are the general basic ones that you always need, which is what are the number of data objects, and then each processor needs to implement this, right? So these are actually a local number on each processor. And then there's this what they call object list, which is just give me the list of the identifiers for these objects, so Zoltan knows how to refer to them later. So these two are very simple, but you always need them. And then there are different sections here for different use cases, like geometric, graph, and hypergraph. And you don't, as I said, you only need some of these, not all of these, depending on what you want to do. So here I tried to make a little checklist of what to do if you want to use Zoltan. So I think first you need to think about, well, what's the problem I want to solve? What is my data, right? What are what we call the data objects in Zoltan? Are they like elements, infinite elements, or is there grid points, or matrix rows, or particles? So that will sort of determine how you're planning to do your decomposition. And then it will be useful to have some knowledge about the different methods in Zoltan. So, well, first you need to know what kind of tools, what you want to do. Typically, you start off by doing some data partitioning, but we also have other things as well. And then what kind of methods you want to use. And this could be a little bit harder to know what kind of method you want to use, but we also provide some guidance at least. Or the next few slides, you'll see some trade-offs between these different methods. So once you have some idea of what you want to do, then you download Zoltan, and you will need to write the required query functions, which is defined by what kind of methods you want to use. And then, well, Actually, I think 5 and 6 needs to be switched here, right? We could, oh, well, okay. Okay, so you have to call Zoltan in your application code. So you need to have a call to Zoltan in your code. And of course, you also need to include the necessary header files, and you need to configure and build it. But it's pretty simple to use because it doesn't have these external dependencies. So once you want to link with Zoltan, actually it's just, you compile like normal and you just add a -l Zoltan at the end, and that's all you need. You don't need to do other things. Okay, so let me go. Okay, so I'm already running behind here. So let's try to speed up a little bit. Okay, so partitioning and load balancing is the main capability area of Zoltan. So I will talk mostly about that. So again, it's how to distribute the data among your processors, and to visualize it, we often use a color coding where each color corresponds to a different processor. So this is one of these classic meshes around an airfoil, and you can see, the blue processor owns this part of the mesh, green processor here, and so on. And if you just did the geometric partitioning, you probably wouldn't get good load balance. But in this example, we used the graph partitioning, so you can actually see that, like in this region, you have a highly refined mesh, so all the mesh points are very close to each other. So there's a very small, there's a small geometric area here, but actually within this pink color processor, or purple, there's the same number of data points as there is in this much larger physical region out here, because you want to balance the number of grid points, or number of elements. Yeah, so, and again, you see different types of structures. And here, for particle simulations, often people prefer the geometric type of cuts. So these green lines corresponds really to cutting planes in a three-dimensional space. And actually, even with geometric methods, you can get good load balance because you don't need to cut it up into like equally sized parts in space. You can make sure that you put your cuts such that you balance the number of particles. And actually, I'm going to show that on the next slide. So yes, question?
Is the partitioning get updated?
Okay, okay, so every time, okay, Zoltan will only compute one partition for what the data looks like right now, right? You have to, you describe the coordinates or the graph that you have right now, and Zoltan can tell you how to do it right now. If you later want to change things, you have to call Zoltan again and provide updated information, and then Zoltan can give you a new partition, and then Zoltan can help you move the data to this new partition. But yeah, this is a good point, that Zoltan can do a lot of things, but it can't actually do everything for you. So you need to sort of decide how often do I want to call Zoltan, and since Zoltan doesn't know anything about the application's data, the burden is on the application to actually move the data, although Zoltan can provide some helper functions to do so.
I have a question.
Yeah.
For example, tree code. Does Zoltan participate in the tree building process? Or it has to be until the tree building process finished and it do the load balancing? Because sometimes the tree building involves load balancing also.
Okay, so what do you mean by tree building?
Like tree code, 3D tree code. So building a tree hierarchy.
Okay, so you think it's something like an octree type of data structure where, okay. No, so Zoltan does not provide functions to build the tree itself, no. So the way you would use Zoltan in that case, you had to build the tree, and then Zoltan can tell you which processor should own which part of the tree. But okay, but Okay, so we do have some function, because I know that some users have asked about this before. Okay, so actually my answer has two parts. So the first part is to say that typically Zoltan does not know about how you came up with your mesh or your data structure, right? You just had to after you built your whole tree that represents your whole mesh, then you describe it to Zoltan, and then the Zoltan will tell you how to move it around. This is the way it normally works. There is some function within Zoltan that is called a tree-based partitioning, where you actually can try to exploit this kind of a tree structure if you have that. It's not something that is widely used, so actually I'm not very familiar with that part of the code. But I believe we do have something like that within Zoltan. And if this is of interest, you can talk to me afterwards, and we can try to look at it.
I have a question also. So for example, also for particles, is there a concept of overlapping domains? Like if you want to have some equivalent of ghost zones, such that particles exist on both processors?
Zoltan assumes a unique ownership of data, so we don't really do the overlap. But of course, many codes do kind of overlapping domains, and they could still use Zoltan, but Zoltan will then tell you sort of who should be the main owner, right? And then you have to do the ghosting using your own framework. The Zoltan does not automatically do the ghosting for you.
No, it doesn't do the ghosting, but does it? I mean, the question was, does it include in its load balancing the fact that you will have?
Oh, I see. Okay, so you want to load balance the local elements plus the ghost and new tree. Okay. That's a great question. Zoltan does not currently do that. That's something that we have talked about. It's actually a harder partitioning problem to solve. So I'm not aware of any of the current partitioning tools that actually support this. Typically what we do is, well, not we do, but what Zoltan users do, is that typically they balance sort of the interior part of each subdomain, right? And then you grow the boundary to get this overlapping region, and then you hope that since your original locally owned part was load balanced, that once you add this extra ghost region or halo around your data, that it's still reasonably well balanced. And in practice, this is a pretty good heuristic, but I agree that it could do better. Oh, okay. So you're thinking of.
That reasoning is probably right, but in case of particles, you may have a clustering of particles, and then it's less.
I see. Okay. Yeah. Okay. I was thinking of more like mesh partitioning, where you do like like a overlapping Schwartz domain decomposition or something. In that case, it would work fine. But I see. Yeah. For particles, where there's a very uneven distribution of the particles, this could be an issue. Yes.
But you had that case, the one that you were showing, the accelerator. How do you do that?
So for the accelerator, we had a lot of particles, but we partitioned the mesh and the particles in two different problems. So we balanced the mesh separately from the particles. Oh, I see. And there was no overlapping there, actually, right? The particles were uniquely owned.
Right. Yeah.
So. Okay, so I'll make a note of that. Yeah, we don't currently have that, but that's definitely something we would consider to add as a feature in the future feature. Okay, and I think I already mentioned a lot of this as I went along. So the two different ways that people often use partitioning is either as a static partitioning, where you only partition your problem once. So you partition your data, you distribute the data, and then you do all your computations, and then you're done. So this is the very simplest case, and you want to distribute the load evenly among the processors, and you want to reduce the communication. But in dynamic or applications, you often have to do this loop, So you can partition, and then you move your data to this new partitioning, and you do some more computation, and then at some point you might find out that, well, now I'm having some load balancing issues, and you want to rebalance, and then you in your application code will actually need to call Zoltan again, right? So then you go back here, and you call Zoltan again, and then you will do another partitioning, and you move your data again, and then You can do this as many times as you like. But Zoltan does not automatically decide when to do this. It is, the application will need to have some sort of monitor to say that, oh, I think I should repartition at this point. That can be sometimes a difficult decision to make. But Zoltan provides a lot of functionality because when you do this kind of dynamic load balancing, the partitioning problem actually is a bit harder because now you want to distribute your data in an even way. You want to reduce communication, but you also want to reduce, actually it's down here, right? You also, the third thing to optimize is you also want to minimize the cost to redistribute the data between the processors because that will also take time. So now we actually get this multi-dimensional, multi-criteria type of optimization problem, which is hard to solve. And I'm not claiming that Zoltan is optimal, but we can do a fairly good job at solving this problem. And then you notice on the bottom of these slides, I have some pseudocode. So Zoltan, or not pseudocode, it's actually real code you can put in your program, actually, but it's one line. It's not the whole example. So we have these parameters in Zoltan to tell what kind of partitioning you want to do. And we have something called LB approach. LB stands for load balancing. So the approach is either partition or what we call a repartition, meaning that you want to do it multiple times and you want to take into account the old distribution and the new distribution. So it's very easy to switch from one to another. The previous slide, I guess I had, yeah, see, the previous slide I just had partition, and if you just change that to repartition, Zoltan will solve a different problem when everything else remains the same in your user code. So what are the trade-offs for partitioning? So since the partitioning problem has multiple objectives and multiple constraints, there's no unique optimal answer, or at least there's no polynomial time algorithm to find the optimal answer. So really we have a lot of algorithms that are heuristic in different ways, and there are all these trade-offs where like quality and speed is really the main trade-off. That if you want something that runs fast, it's not always good, and if you want something that is good in terms of load balance and communication cost, then it's going to be more expensive to compute. Yeah. So and we have several algorithms that provide different results or different trade-offs on this, and it might not always be easy to know which one to call, but if you use Zoltan, at least it's easy to try different things. So you don't necessarily need to know upfront what will be the best thing, because once you implemented these Zoltan query functions, you can just change a parameter and you can essentially try 3 or 4 different strategies and see which one works better. And so that's really the value added by using the Zoltan. So it's a suite of partitioning methods, not a single method. And the way you change the parameter to do a different method is you just do this Zoltan set parameter and the load balancing method, and then it's a string that could be graph partitioning or hypergraph partitioning or recursive coordinates bisection or something like that. Yes?
Yeah, how extreme does it go? If I have an application where I'm doing all of my partitioning offline, are there some algorithms that would be better? If I really, really, really care about optimizing my online performance and I know my partitioning is going to be the same, are there appropriate algorithms where I can invest a lot of computation in partitioning?
Yes. I would say that the method that probably, or in most cases, produces the best results but the longest time to compute, which I think is what you're asking about, is our hypergraph algorithms, because they take into account sort of the exact connectivity pattern between things and tries to optimize things. It's similar to graph partitioning, but it's a little bit more sophisticated model, but it also takes longer time to compute. So that's what I would recommend for you if you're willing to spend a lot of time. Some people don't want to use it because if you do this at runtime, your application actually has to stop and wait for the partitioning to compute something. Then you don't want to do the hypergraph because it takes too much time. But if you do it offline, I think that would be a good option. Okay. Oh, okay. So here actually is a slide where we describe a little bit about the different types of algorithms we have. So we have geometric algorithms. The most popular is known as RCB, the recursive coordinate bisection, where we just use these straight cuts through geometric space. We also have space filling curves, which work in this recursive, funny way. And then what we used to call like graph algorithms, but since we've extended it to work with hypergraphs, which generalizes the graph model, we now call them like combinatorial or topology-based methods. So, and in fact, it is a hypergraph method and a graph method. Some of these. Oh, so one thing is that I hadn't mentioned. Actually, I'm glad it came up on this slide. Is I said Zoltan is a self-contained piece of software, and this is true, but there are also other very good tools to do partitioning. For example, the Parmetis suite of tools and the Scotch suite of partitioning tools. So since we don't want to replicate or duplicate other people's work, we also provide interfaces to these libraries as external pieces of software. I think that's why it's color-coded to be purple color down here. This means that these are external, what we call third-party libraries. So you could use Zoltan with these codes as well, but you would need to compile and install it separately, or on the NERSC system, they would already be installed, so actually you just link with it. So this adds to the value of Zoltan that we have a common interface, and you could use Zoltan-specific algorithms, or you can use these external methods using as a third-party library. Okay, so let's. Okay, so I think I'll fly through sort of what do these different types of algorithms do, because I don't think you need to know all the details about these algorithms, but you just have some vague idea of what the pros and cons are. So the geometric algorithms, well, first of all, it assumes that you have some geometry in your problem, and that using spatial locality is a good idea. And as I said, the RCB will use these straight cuts. The space-filling curves will go around in like circles, or not circles, but in its recursive fashion. And in our experience, RCB tend to be very fast to compute and produce reasonably good results. So a lot of people actually prefer this as the default setting. The way it works is it is a recursive algorithm. So you will first find like one cut to say that, okay, what do I mean by cut? Is that we now partition your space into two parts. So there's a right-hand side and a left-hand side. On each side, you have half of the data, right? So if you had two processors, this would be what you did. But typically, you have much more than two. So then you have to recursively do this on the right-hand side. You can do a cut now possibly in a different direction to split again into two parts. And then on the left-hand side, you can also do a cut to split into these parts. So, yeah, I think. Okay, this slide was supposed to be dynamic, but it didn't quite show up that way. But that's okay. So, but this is the idea that you do this recursive bisection, and this can give you better low bounds than if you did sort of cuts that were. Okay, so what you get in the end is something that looks a little bit jagged, right? That's what you notice, that this horizontal line actually doesn't go all the way through the domain, because you have a horizontal line here and a horizontal line there that are a little bit offset. And this is the good thing, because you can get better low bounds than if you had just like a cross in the middle here. So that's why we want to do this recursive bisection instead of just doing it all in one big shot. And this is used for lots of different applications. Often when you want to have like dynamic adaptive type of applications, you want to do some method that is very fast, since you do it actually in real time at runtime. And that's why RCB is quite popular to do within these types of problems where you actually need to do dynamic load balancing at runtime. And then, yeah, so advantages of geometric methods is probably the easiest type of method to use. Okay, question.
Regarding the adaptive mesh, are you doing the adaptive within Zoltan?
No. So this slide was just saying that these are applications that could use Zoltan this way. Zoltan does not have like a mesh refinement type of capability in it. It's more designed to work with other codes that already do mesh refinement. So
any recommended mesh refinement libraries that Zoltan would work well with?
I know that it works well with well, I think it's still called ITAPS mesh refinement. This is a DOE SciDAC project. They have, yeah, if you Google ITAPS, ITAPS, they have a lot of meshing tools and mesh refinement tools, and they have interfaces to Zoltan. So that might be one way to get a code that can do both mesh refinement and Zoltan at the same time. But yeah, Zoltan is really sort of decoupled because often there are existing software projects that have their own data structure and their own mesh refinement, and they just want to use Zoltan. So that's then in that sense, Zoltan is sort of more lightweight. It's not really a complete framework to provide all the capabilities in this area. It's just to do the partitioning and the load balancing.
So does it force us to have different levels in the same process, right? As you're refining your domain, does Zoltan make sure that the data, which is at different refinement levels, is belonging to the same processor? I don't know if you understand my question.
I'm not sure I understand it actually.
So you have domain, and then you're refining some patches.
Right.
So does Zoltan make sure that so when the patching is how it distributes patches that are refinements of some coarser patch? So does it put them on the same processor such that you have vertical hierarchy on the same processor, or it can be distributed?
Okay. So now I guess I should repeat the question since there's no microphone over there. So the question was, when you do adaptive mesh refinement and you have these different levels in your mesh data structure corresponding to different levels in the refinement, whether the data stays on the same processor or if they had to move. Okay, so the answer is that Zoltan tries to take this into account because okay, so this goes back to the slide I had about the repartitioning or dynamic load balancing. When things change, like in adaptivity would be what we consider sort of a change in your data structure. So it will try to keep things locally to the same processor as much as possible. But because of the load balancing issue, if you have like one processor that does a lot of refinement, but the others don't, then obviously this processor gets too much data and you need to move something to neighboring processors. But the Zoltan will try to minimize the data transfer cost by moving the data. So everything is kept local as much as possible.
I guess a follow-up to that would be, if it tries to keep it local, can you specify that you want to keep it local in MPI rank space? So maybe you stay close by on nodes, like on the same node, or you know what I mean?
Oh, are you thinking of like in a multi-core type of architecture? We have, to some extent, that's actually something that we're currently working on now, is like incorporating like a machine model into this load balancing problem, because, okay, so originally Zoltan was developed for a distributed memory model where all communication costs are the same, right? That every, you have a unique flat network structure, and every message takes still the same amount of time. But with modern architectures, you really need to take into account sort of the on-node cost versus the inter or intra-node type of cost of communication. And so that's something that we're currently working on. There is already some features in Zoltan where you can provide like different types of cost functions to account for this, like using like a weight. So if you know that two things are close to each other, you have a shorter communication time than things that are far from each other. But right now, the user has to provide some of this, and we have a research project right now where we're trying to do some more automatic discovery of what your machine looks like, and more tighter integration with the architecture and the network, the system performance, to try to do this kind of load balancing, like we call it like architecture-aware type of load balancing. And that's something that we're working on, but it's not in the currently release.
You don't have a direct mapping to the MPI task to the core.
Yes, that is a problem. We don't. That's one of the things we have encountered, is that you don't really know which MPI process is running on which node, right? That it's hard to find out actually if two MPI ranks are running on the same node or on different nodes.
So even if you're in the same node, let's say that you discover that you're on, if you could tell that you're in the same node, the problem is that the cores, the configuration inside the node may hit you.
Yeah. Okay, sorry. Okay, so that's a great question, and I realize that I'm totally behind schedule here, so I'm going to skip a lot of stuff here. So, graph partitioning, I think a lot of you are familiar with it. You have data elements. You represent your data as vertices in a graph, and then you have edges between data that corresponds to data dependencies and communication, and then you try to minimize this graph cut objective using this combinatorial graph type of model. And this has been used for many years, and it works for a wide range of problems. There is already existing software that can do this, but Zoltan, I think, mainly adds value by having a common interface to a lot of these existing partitioning tools. One of the things I want to point out, though, is that graph partitioning is a little more expensive than geometric methods. So if your geometric method works for you, then you might want to just stick with the simple method. But also, that a lot of people think that once they do graph partitioning, that this minimizing the edge cuts is actually exactly what they want to minimize. But really, it's not an exact model. It's only an approximation. So it only approximates what we call the communication volume between the processors. And if you really want to get a more exact and higher quality method, you should go to what we call a hypergraph partitioning, which actually now I don't have time to really go through in detail, but I just want to say a hypergraph is a generalization of a graph model, and the main advantage of a hypergraph versus a graph is that it takes into account not just, a graph is only pairwise interaction, so A is neighbor to B, B is neighbor to A. A hypergraph, you can have connectivity between multiple things, so like A, B, and C can all be connected through what you call a hyperedge. So this gives you a more accurate representation than just a graph model. But then to do hypergraph partitioning is a harder problem computationally, so it takes longer time. But we have this in Zoltan, and that's one thing that sets Zoltan apart from some of the graph partitioners, is that we actually have a hypergraph partitioner, and one that runs in parallel, which actually no other software has. And it does, and we also, in addition to the normal partitioning model, we also can do this repartitioning, which is what one question came up, minimizing the data transfer between things. And we also integrated that into our hypergraph models, so you actually can do hypergraph partitioning for these dynamic repartitioning problems as well. And this you can do for the same type of problems you do graph partitioning, you can do hypergraph partitioning, and you'll get slightly different results and slightly better application performance, but it takes longer time to partition. That's what you say in advantages. Disadvantages, usually more expensive to compute. And these colored charts that are flying by shows that if you do hypergraph partitioning, you have to implement a different set of query functions than if you did the graph partitioning. So yes, if you want to try different methods, you might have to implement a few more functions, but these functions are pretty easy to implement, so I don't think it's a lot of work to do so. Here was this question about multi-core type of systems. So let me just spend the last couple of minutes on this slide, I guess. So now systems often have this hierarchical structure where you have compute nodes, and within compute nodes you might have sockets and cores and so on. So you can think of this as a hierarchical structure that represents your machine, and now you want to not just minimize communication, but you want to keep things local within this sort of tree-like machine data structure as well. And actually, we do have some working code in Zoltan to do this. So when I said we were working on it, that's true, but there is already something in the release version that you could try today. And it's what we call a hierarchical partitioning, because we're thinking of this machine tree as like a hierarchy in your system. And we have a parameter now called topology, which corresponds to the topology of your machine and not your data. So I'll throw as an example. We actually ran on the Hopper machine here at NERSC, where you have each node has 24 cores. And we ran an example where we had 96 subdomains or parts so we can do one per core, but not all cores are the same, right? So that's actually what we wanted to see, was that what is the effect of doing this kind of hierarchical partitioning where you try to take into account the machine model versus just ignoring what the machine looks like. So if you just say topology equals 96, that means that we have sort of a flat model that you're 96 cores and you know nothing about how they're connected at all. But you could say topology equals, and then this is like a list, right? So 4, 24 means that you first have 4 nodes, and within each node you again have 24 cores. So what Zoltan then will do is it will first partition into 4, first partition for the nodes, and then within each node you can partition for the cores. And you can actually do this in multiple levels. Or typically we only do like 1 or 2, but you could say, for example, on the Hopper where you have 24 cores, but actually there is more locality too, because there are like 2 sockets and 4 dies. So you can actually subdivide within the node as well. So you can do like 4, 2, 12, or you can do 4, 2, 2, 6. And the only thing is that, you know, if you multiply all these numbers together, they should add up to the same thing, right? So we did some experiments on just running a simple kernel. Let's see. OK, so this was a sparse matrix times vector kernel, because that's often the computational kernel in many types of applications. And we ran on different types of matrices from different application areas. And OK, so here the chart is runtime, so lower is better. And what we see is that the blue one, so we normalized it, so the blue one is always equal to 1. So this is, if you don't know anything about your machine, this is sort of the default way that Zoltan works. But then you can try to give more information about the hierarchy, and you can, and what we see is that if you go from 96 to this 4 times 24, where you actually make your partitioner node aware, then you can see that the runtime for the Mat-Vec goes down. Sometimes like 10–15%, but like in this case, it went down by about a half, which is fairly dramatic. So definitely partitioning for the nodes seems to be a good idea. But then if you try to exploit the locality within the node by using like sockets and so on, then actually that doesn't seem to pay off very much. But this will depend on how your application code is written. So I think this code was a fairly simple type of Mat-Vec code. So it was not so easy to exploit this kind of on-chip type of locality. So I think the advice I would give is that if you want to try to get some better performance, you can try this hierarchical partitioning using the 2 levels, the nodes and number of cores within the node, and that has a good chance to give you some extra boost in performance. Okay, and I think I'm out of time. Is that right? Yeah, well, like, okay, a couple more minutes.
We have a long break. So.
Okay. Well, I'm not going to keep you too long, but I realize I'm way behind. So I'll fly through the last few slides here. So in addition to the partitioning and load balancing that I really focused on, because that's what most people use Zoltan for, we can also do different types of ordering problems. So this means, if you have a sparse matrix or a graph and you want to reorder your data to get better performance, that's what we call by ordering. And we have different types of ordering for like fill-reducing ordering for sparse matrix factorizations, or we have data locality-based orderings to get better like cache and memory performance. And again, I don't go into details on this, We have also something called graph coloring, where you can find independent subtasks by different coloring, like red-black ordering is a common thing in numerical methods, where you compute on the red points and then on the black points, and you can alternate. And a more general model is graph coloring, and Zoltan provides parallel graph coloring using a couple of different types of algorithms and models for coloring as well. We have different interfaces. What the default interfaces you get are C, C++, F90, but you can also download other software to get sort of higher level types of interfaces. Like there is mesh-based interfaces in the ITAP software that I mentioned. There's also a Trilinos package called Iseropia that provides matrix-based interfaces for Trilinos users. It's only really valuable if you're already using Trilinos. Okay, and so yeah. I don't think I want to go through this, but this is just, if you are a Trilinos user, you don't actually need to do these Zoltan query functions that I talked about in the beginning, because this Iseropia package already has predefined the right query functions to work with Trilinos data structures. So if you have like an ePetra matrix, you can use this Iseropia ePetra partitioner, and it will know exactly what your matrix looks like, and you can just set some parameters, and then you just say partition, and then it will just work. So this is like a very simple entry point if you're already using Trilinos. But if you're not using Trilinos, you have to write your own query functions. And then, okay, so this is the last slide, I think. Just mentioned that Zoltan has been around for about 12 years, and it has worked well, and we're going to continue to maintain Zoltan. But as part of this Trilinos project, we're moving to a more newer version of C++ using more templated data types. And to accommodate that, we decided that we're actually going to have a new project we're calling Zoltan 2, like the successor to Zoltan. And it will provide much of the same functionality as Zoltan does, but it's a new code base. It's going to be written using like templated C++ and be more tightly integrated with Trilinos. And one major objective is to support large, more than 2 billion elements, because some people are running into this 32-bit limit. And Zoltan was really designed to work with 32-bit machines. And templating is a nice way to allow 64-bit and 32-bit to coexist at the same time. So you can say my index type is int, or it's long, or it's int64, or whatever kind of indexing type you wanted to use. So this is something that we're working on, but it's not released yet. So I just wanted to mention it. So then I'd just like to thank the rest of the team, especially Karen Devine, who's actually the Zoltan leader, and a lot of other external collaborators have contributed to Zoltan at Ohio State and MIT Lincoln Lab, and also in France. So it's really a large collaborative project. If you need to find more information, we have a good website, and you might be interested in the Trilinos Fast Math homepage, where also Zoltan is a part. And we have an email list if you have specific questions for the developers as well. So I think, yep, that is the end. So thank you.
Any questions for Eric? Any more questions? Can you hold? It's just that then the people that are online, they can.
Are you planning anything for Python users?
So currently there's no Python interface to Zoltan, but you could do it in an indirect way, actually, because Zoltan is part of Trilinos, and there is a PyTrilinos, like a Python wrapper on Trilinos, and I believe that the way you could use Zoltan would be using PyTrilinos, and then this package I mentioned at the end here called Iseropia, which is this Trilinos wrapper around Zoltan. So within PyTrilinos, you can use Iseropia, and Iseropia will then call Zoltan to do things. But it's a kind of roundabout way. Currently there's no direct Python wrapper around Zoltan.
You also have a number of Fortran users. So what
Yes.
will happen when you move to the Zoltan 2? Are you planning to have the Fortran bindings? I mean, Fortran 77, because you have codes then.
So I think the answer is probably no. Probably Fortran users will be stuck with the current version of Zoltan because, well, unless there is some new version of Fortran that can support templated data types, right? Because otherwise, I don't know how to do that in Fortran.
Right.
But that's why I want to emphasize that the current Zoltan will not go away. So
Right,
you can start
right.
using it, and it will still be around. I view Zoltan 2 as to complement the current Zoltan and provide new features, but the old things will still stay there. It just won't be actively developed anymore.
Mm-hmm. Okay, so let's thank Eric again.